What's up, Algebra 2.1? This is Mr. Carlson with C-Squared Mathematics. What we are going to be doing today is 3x3 linear systems. They're a little bit different than 2x2 linear systems. That's what we learned previously. So we're going to see why they are different, how they are different, and of course we're going to solve them. We're going to see if we can solve them graphically, algebraically, all that fun jazz. Let's go through bell work. So you are adequately prepared for the homework quiz, 2x2 linear systems. We're going to go through the objective, essential question, then the actual lesson for 3x3s, and then of course closure homework. These are the only two questions I have for bell work. Okay, they will be on the homework quiz, or at least one way, shape, or form. Definitely this one will be on the homework quiz, and I believe the second one is on the homework quiz. So pause the video, make sure you get them down so that you can reference them on your quiz. Let's go through this one first. So let's read it together. A rectangular lot whose perimeter is 300 feet is fenced along three sides. An expensive fencing along the lot's length costs $24 per foot. An inexpensive fencing along the two side widths costs only $4 per foot. So notice sort of what's happening here. Okay, first of all, it's three sides. Second of all, there's only one length. And third of all, there's two side lengths. So automatically, we can kind of develop this little picture here. Okay? So we can develop this. I know that my perimeter is 300 feet. And let's just say off to the side, let's just say X will be your width. And then your Y value is your length. So that means this is Y, and this is X, and this is X. Now technically this is Y as well, but wait. Before we even finish the problem, we notice it's only three side lengths with one length and with two side widths. So that means what I'm highlighting in blue here is the only sides I'm interested in. Only that one width right here and these two side widths. I don't care about this at all, that Y, I don't. So what I really want to do is focus on those three sides. So let's continue. The total cost of the fencing along the three sides comes to a whopping total of $2,480 plus $80. So $2,480. What are the lot's dimensions? Okay, so this is basically in feet. Like, what are the lot's dimensions? Okay, we want to know how long this length is, how the size of the widths. How long are they? Okay, so that's feet, not dollars. So let's kind of develop this. Now, this was from 2x2, so you know you're going to be using some sort of 2x2 linear systems. So the first one I have is actually very easy. It's the perimeter function. And that is if I add both my widths up, so x times x, x plus x is 2x. So if I add that up, I get 2x plus y plus another y is 2y equals 300. Now, you may be asking, why am I using this y if I don't really know what it is? Because technically, I need to say that the whole lot's perimeter is 300. Now, if I just had one y here, well, that's not right, correct? Like, that wouldn't be a total of 300. So that means this whole thing, when I add it together, equals 300 feet. Okay? Not just the three sides, but the whole thing, including this side that I'm not taking, that I'm not trying to fence, is 300 feet, okay? So in order to find what these three side lengths are, I need to include a different equation. So my different equation is this. Now let's read carefully. An expensive fencing along the lot's length costs $24 per foot. Now I want to know feet, right? So I know y and x is the width and the length in feet. I want to know feet, so it's $24 per feet. Well, per means times. So that means $24 per 24 feet, okay, per foot, all right? So it's 24 feet, $24 per foot. So plus, I want to add that to my other widths here. So let's read on. An inexpensive fencing along the two sides costs along the two sides costs two different, well, they cost the same, actually, now that I'm reading it. So two side lengths cost only wow, I keep saying two. Two side lengths cost only 4 feet, $4 per foot. Man, I can't speak. Two side widths cost only $4 per foot. What does that mean? Well, $4 per foot just means multiply it again. So 4 times x, because that's my width. Now watch, it's two of them though. So it's not just 4 times x, it is actually 2 times 4 times x. Because I not only take the $4 per the foot with my width, my x, but I also have to multiply that total by 2 because there's 2 of them. We did not do that here because there's only one length that I was interested in. Here there is 2 widths that I'm interested in. Now if I do my money function right here, if I add all that up, what do I get? When I get the 3 sides total, when I do the 3 sides total, I get 2,480. Okay? So now what do I do? Well, I can simplify this, which I will. So this is 2x plus 2y equals 300. And then let's simplify this. 2 times 4 is 8x. And then plus 24y equals 2,480. So this right here is my 2x2 linear system. So now I can solve for x and I can solve for y. Now, can I do this by hand? Absolutely. Will I do it by hand now? No. The only reason why I'm not going to do it by hand is because we have a lovely tool. You may have heard of it in this class. It's called Desmos.com, in which I can plug this in and I can actually find the intersection point. Remember, the solution to a 2x2 linear system is the intersection point. So that's what I'm going to do. Now, could you solve this by hand? Yes, you would multiply the top by -4. So you'd get a -8x. The x's go poofy. You solve for your y. You substitute back in to solve for your x. Now, why would you want to do that when you're timed on a test? You need to go fast. You want to utilize all your resources. You can utilize an amazing resource called Desmos.com. So let's go there and type it in. Now, you may say, well, Mr. Carlson, this is cheating. It's actually not. Number one, because I'm telling you to use it. And number two, it's because you're using your resources. Now, you may say, well, what if I'm using my resources with my older brother or sister or by paying someone else to do my homework? Am I utilizing my resources there? No, because it's not your own work. Okay, it's not your own work. Now, what if you say, hey, am I utilizing my resources by looking it up on Mathway? No, because again, Mathway solves it by algebra. You're not solving it algebraically. Okay, so it's still not your own work because it's not your own algebra. But if you plug it into Desmos, you are plugging it into Desmos. You are doing the work. You are solving it graphically. So it is your own work. So therefore, it's not cheating. You feel me? Now, I plugged it in exactly how we had it, right? And you may be wondering, well, what the junk? There's nothing here. Desmos is broken. Be patient, Grasshopper. Just zoom out a little bit, okay? You zoom out and then you start seeing something marvelous. You start A, seeing your 2 lines, but B, you start seeing an intersection. What is that intersection point? 70, 80. What's my answer? That. So my x is 70 and my y is 80. What does that mean for us? So that means when I go back, my x equals 70 feet, okay? Whereas my y equals 80 feet. Now, does this make sense? And these are my answers, by the way. Yes, it should make sense. Why? Because A, your width has to be shorter by definition of a rectangle, has to be shorter, not equal to or greater than, but has to be less than your length. Is x, my width, less than my length? Absolutely. Okay, it's a rather fat rectangle, okay, but a rectangle nonetheless. Okay, it is still a rectangle. All right, and then of course your length has to be greater than and that is true. It's greater than. So it's greater than my width, which is 80. Okay? So that means it's 80 right here, and then each side is worth 70. So if I do 70 plus 70 plus 80 plus 80, I get 300, which is my width, which is awesome. Okay, I can just plug it in here to double check it. So that is how you do that question. I'm sorry I didn't do the algebra, but you should be very familiar with Desmos.com in order to plug it in here, and so you can get your answer right there. Okay? Awesome. So let's erase this. Let's go to my next one. I am going to solve this one by hand, but before I solve it by hand, I'll give you a second to copy down, and then I'll also go to Desmos. So it says solve the system by the addition method. Now we will. The addition method is the same thing as elimination. Now I want to show you though on Desmos what we will actually get. Now some of you may be thinking, well, I can do all of this on Desmos. Think again. Sometimes you can't. Okay. So let's try it. So this is 2x. Let's just plug it in. 2x equals 5y and then plus 1. Now this is 4x and then equals 7 minus 7y. So a lot of lines are happening here. Oops, I accidentally did C. Let's get rid of these. Let's do Barney colors. Okay. So now, these are my lines. Now if I try to zoom up, let me zoom up here. This is where they intersect. Now, that's a decimal. Okay? There is technically a way, and this could honestly work because I haven't tried it yet, at least with this problem. So there is technically a way to plug this into Desmos and try to get fractions. So let's try that. Even if it does work, I'm going to go back and actually show you the real answers. So this one, my x was 1.235. So let's type that in, 1.235. And the only way that I can think of to get a fraction here, because that's what Math Excel wants, is a fraction, is to click on this fraction button right next to it. Oh, yeah, see, then you get that, and that is definitely not the answer. Okay, I know, I have the answer. So unfortunately, that will not work, okay? So let's try to do the other one. What is this? 0.294. So 0.294. Let's try to click the fraction button. Yeah, see, that does not work. Those are just obscene fractions, really annoying fractions. Okay, if you put that in Math Excel, I'm not going to give you the credit at all. And Math Excel won't even give you the credit. But even if you ask for partial credit, I won't give you the credit. So this is a question that we need to do by hand, okay? Because you see here there's decimals, and you can't put in decimals. It needs a fraction. So unfortunately, you cannot use Desmos for everything. Let's go back. Let's solve it by hand. The first thing I want to do is put them in standard form. So 2x minus 5y equals 1. This is 4x, and then plus 7y equals 7. We already know we're going to get fractions. Okay, so that's good. What are we going to do here? Well, the first thing I notice is my x's are probably the easiest because I only need to multiply this one by -2. Instead of, if I wanted to eliminate the y's, I would have to multiply both of them by 5 or 7. So now my new one is this, -4x, and then I multiply this to everything, make sure you do that, plus 10y equals -2. And then my new line that I didn't change, that's still in red, is 4x plus 7y equals 7. So then I add them, that goes poofy, this equals 17y equals 5, so y equals 5 all over 17. Okay, now let's go back to Desmos and let's actually type that fraction in, 5 all over 17. Let's do it. I get this. Now, obviously, you see this? So this right here is 0.294, just like this. But the problem is this, guys, it's not actually, like, it's rounded. Desmos rounds it right here, okay? So that's why it's giving you a different fraction. But wait, what if I start adding this to it? So 0.294117647 and so forth. And then you start going, and you can't even do it that way. So it doesn't even register a fraction that way. So unfortunately, the only way we can do this is by doing it by hand, algebraically. Okay, so let's finish it. I have this fraction. Let's plug it into, it doesn't matter. Let's just do it this bottom one. So let's do 4x equals 7 minus 7 times 5 all over 17. Okay, so this is 7 minus, this is over 1, so negative 35 all over 17. And technically, I still have a 4x there. Now, what do I do here? I do have to combine fractions. And so combining fractions, remember, this is over 1 times 17 gives me 17. 1 times 17 is 17, right? What is 7 times 17? Okay, 7 times 17 should be, I think, I can't even remember. 7 times 17, 119. I was close. I was thinking like 120 something. So 119, I just don't want to be wrong. So 119, and then we minus them. 119 minus 35 is 84. So far what we have is 4x equals 84 all over 17. Now we could do that because we had common denominators. Now I'm going to multiply this by 1/4, not divide by 4, because divide by 4 would do nothing. I already have a fraction. I would have to multiply by the reciprocal regardless. So that goes poofy. So now I'm left with 84 times 1 is 84. And then 17 times 4. 17 times 4 is 68. So this can clearly be reduced, 84 divided by 68. So let's see what it can be reduced to, all right? And so when I go back to decimals, 84 divided by 68, let's try this. So 84 divided by 68. Now this does give me the same decimal that I had before. That's amazing, right? So 1.235. But now let's simplify it, turn it into fraction, and now that is a better fraction. That's way more simplified. So 21 all over 17. That is my answer. So let's go back. 21 all over 17. So I know this is kind of lame because of fractions, but you still get the right answer no matter what. So this is my total answer. And of course, an amazing unicorn to help out with our good math. Okay, so that is the bell work. Make sure you take a picture, get it written down so you know what to do for the homework quiz. Let's race. You will have 25 minutes, 5 questions. Please review your answers. Send any partial credit requests to me if necessary, if you need to. You don't need to, though. And then begin your Cornell notes today for 3x3. I only have 4 examples for these Cornell notes. 4 examples. Okay? So, without further ado, after you complete that, let's get started on 3x3s. All right, what's a 3x3? Well, first of all, how can I solve a 3x3? What is it? Well, it's 3 equations, 3 variables. Think about that. 3 equations, 3 variables. So you can have a 4x4, a 5x5, a 10x10, a 11x11. You can have tons of these equations, okay? And there are amazing ways to solve them using computers. I'm not going to teach it to you now, but if you want, you can figure out an awesome way to, I'm not even going to give you the name. It's an awesome way used in pre-calculus to solve 3x3 linear systems. And if you take pre-calculus with me, I actually teach you that way, okay? But now we're just going to do it by algebra, or algebraically, and I hope you don't get mad at me. So how do I solve 3x3, and why can I not solve them graphically like 2x2s? Okay? Yes, like the squirrel, you can have a system of 5 equations, 4 unknowns with the correct solution set the first try. As you will notice, as we go through these, it's going to be very difficult to try to get to the answer without doing some sort of algebraic work. So make sure you have lots of room on your notes. Make sure you're taking notes, okay? So an equation like this, x plus 4 equals y. Wow. Flip them. X plus y equals 4. X plus y equals 4. Graphs to be a straight line, obviously. when you graph another equation like negative x plus y equals 6, they intersect. Where do they intersect? Okay? But we call this a linear system. In fact, we call this a 2x2 linear system. So where do they intersect? Well, let's plot. I don't know. I don't really care exactly where, but I'm going to plot the intercepts. So the intercepts for y is 6 for this one right here, my red line, and then same thing for it's going to be negative 6 for my x. So it will look something like this ish. For my red line, I'm just plotting the intercepts, plugging in 0 for each x and y, and that's what I get. And then if I wanted to do my blue, both of them are 4, so that means 4 and 4. So they're going to cross somewhere around here. Maybe that's the point, negative 1, 5. Possibly. I don't know. I'm not going to check it, but that's possibly the point. The whole point is this, though. Get it? Because it's a point. The whole point is this. They will cross somewhere on the XY plane. Okay, that's what we did just yesterday during the video. So what do you now think, though, about x plus y plus z? Okay, what's the difference? Well, first, it's a z. And secondly, can it even be plugged into a two-dimensional plane? And this is the problem. If we were to graph two other equations like this, what do you think the solution would look like? Think about that. Would it be 2D? No, it wouldn't be 2D. I have a 3D printer in my room. I don't know if you guys knew that, but I have a lovely 3D printer in my room that I won last year, actually, or 2 years ago. And when I'm going through trying to print something, it gives me an axis that looks something like this. I'll try to draw it. Okay, where this is your x, this is your y, and this is your z. But they still intersect. So it's kind of like a point system here. I'll try to draw it like this. Okay. So there is like a three-dimensional plane here that they have to intersect at, okay? And I build my 3D models on that three-dimensional plane, like in my program, and then it renders out a three-dimensional thing. So, for instance, I have built my lovely Abraham Lincoln on a 3D printer. He's very lovely, okay? I've also printed this. A unicorn. Who would have thought, right? And then I've printed also many, many other things because, you know, I'm vain. So I printed this as well because, you know, I love Spider-Man. Now, obviously, the color did not come from the 3D printer. I had another student paint it for me. They wanted to paint it. But this whole thing is 3D printed. Yes, I'm not lying. It took at least 13 hours, okay? So, yes, it's 3D printed. Yes, you can do it. So what does this mean? This means we're not doing a 2D, we're doing a 3D. Okay, so can you solve a 3x3 linear system on a two-dimensional plane? No. Which means, can we use Desmos? No. Which means this is very hard. Okay, this is very difficult, so you need to pay attention. This can get very, very complicated, which means because it can get complicated and because I'm so nice, I gave you some of the best steps ever, okay? What are these steps? First of all, example 1, we're going to look for what we call a bonus. What's a bonus? A bonus is when you add two equations together and eliminate. We eliminate two variables. That is amazing. If you can do that, wow. You know, if you have a bonus, you can add two equations together and eliminate two variables, so you already have the third one. That's awesome. If that's the case, you're going to solve for the remaining variable, the one variable that you're solving for. After that, you're going to add any two other equations together to eliminate one of the other variables. I've tried to be as specific as possible on these steps, as you can tell, as they've kind of formulated over the years, okay, as to promote no confusion. Now, after that, you're going to substitute the value from 1a, whatever you got there, and then solve. And then after that, you're going to substitute the values from 1a and 1c, solve, into an equation and solve for the third variable. So we're going to be given something like this. Okay? So write it down. Let's think about what we're going to be doing here. The first thing I want you guys to start getting in the hang of is labeling them. Okay, so this is equation 1, 2, and 3. Because it's so much easier to label these equations, 1 or 2 or 3, because you're going to manipulate them, you're going to transfer them, you're going to be looking at it's going to be really confusing when you're in the heart of algebra to know which equation you're actually going through. So 1, 2, 3. Now let's look. Is there a bonus? Can we add 2 equations together and eliminate 2 variables? Well, it just so happens we can. What are those 2 variables? X and Y, right here. The only thing we need to do is just change one of them. Just change one of them to make it a negative. So it doesn't matter which one. I'm just going to choose the second one. I'm going to multiply this by a negative. So what are my new equations? Okay. My new equations are this. So I'm going to do 2 and 3. Okay, or sorry, 1 and 2. I'm going to do 1 and 2. So that means 1. Do I do anything with 1 right here? No, I don't. I just chill it. You know, it's just chilling. I do change 2. So 2 is changing here. Okay, actually, let's just keep it in blue. And so now it's going to be negative x minus y minus 9z equals, and then positive 9. When I add this junk up together, what happens? We'll do this in red. That goes poofy, that goes poofy, and I'm left with negative z equals 1, which of course is z equals negative 1. So now I have one variable. What did I just do? I just did 1a. Okay, that's the step I did. So 1, I looked for a bonus. Sure, I eliminated one thing, so I solved for the remaining variable. I took 2 equations at a time. I didn't take all 3. I took 2 equations at a time and eliminated the variable. Okay, 2 variables actually, and I got z. Now, does that help us? Well, I have z, but how do I find y? It's not like I can plug z into the equation to find x and y simultaneously. So we had to follow the steps. 1b says, add any other 2 equations together. What other 2 equations together? It really does not matter, but what I notice is that I can do 2 and 3. Why? Because if I multiply, let's just say 3 by a negative, okay, I can eliminate the x's. I can do 2 by a negative. I can multiply 3 by a negative. I can multiply 2 by 9 and eliminate the y's. But that would also make these big numbers. You know, I don't want to do that. So here's what I'm going to do. I'm going to do 2 and 3. There's more than one way to do this. Like, as one of my geometry teachers once said, there's more than one way to skin a cat. And oddly, that's kind of scarily true. You know, we can skin a cat many ways. So I'm going to just leave 2 the same. So plus y and then plus 9z equals negative 9. Now the next one, I'm going to actually multiply this negative through. So my 3, I'm going to multiply negative through. Equals 27. And so when I do that, I'm going to kind of do 2 steps in one, okay? So I'm going to, in red, I'm just going to multiply by the negative. Ready? So that becomes a negative, positive, negative, negative. So what happens to the x's? Now I'm eliminating a different variable. Eliminate one of the other variables. I cannot eliminate z. Do you understand? I can't eliminate z because that doesn't help me. Then I'm just left with y and x. But I need to have z in one of these equations so that I can plug it in. So x is eliminated here, and now I have y plus 9y, which is 10y. And then this becomes plus 6z, and then equals negative 36. Okay. Now what I can do is I can take z in and plug it, which is step 1C. Substitute the value from 1a, which we got -1, and solve. So this is 10y plus 6, and then I'm going to multiply this by my substituted z, -1. And now I have equals -36. So what do I have? I have 10y, and then minus 6 equals -36. I have 10y. I add the 6 over, so that gives me -30. And so y, when I divide by 10, gives me -3. Okay? I have -3. Now I have 2. Awesome. What's my last step? Substitute the values from 1a, which we got -1. And then from 1c, which we got -3, into any other equation, any equation really, and solve for the third variable. So which one's the easiest? Let's do 1. Okay, so let's go back. Let's do 1. What is x? I don't know. But what is y? It is -3. What is z? -1. So plus 8 times -1 equals -8. And so this is x minus 3 minus 8 equals -8. Okay, the 8's do go poofy because they're the exact same number. So I'm left with x minus 3 equals 0. And then now x equals 3. That is my final answer. So what is the total thing, what it would look like in 3 dimensions? 3, comma, -3 for y, comma, -1. This is my point, my intersection point for my 3-dimensional plane. Okay, so does it take a lot of work? Well, obviously, yes. It does take a lot of work, okay? But you have to solve it by hand, guys. You can't solve it using Desmos. There is a way to solve it using higher level mathematics, but I'm not going to teach that to you until you get into pre-calc, okay? So let's go on to our other 3 examples. They're going to be harder, though. So let's erase. The steps are going to be a little bit different. So first step, look for a bonus. Obviously, that's the easiest thing to do. Okay, now what if we don't have a bonus? Now, what we do, no bonus, we would add any 2 equations to eliminate 1 variable. Add any 2 equations to eliminate 1 variable. Okay? Third step, add 2 different equations to eliminate, here's the difference, guys, the same variable. So before, we had to do the same thing, but eliminate a different variable so we can substitute that z in. Okay? But this is, you're going to eliminate any 2 equations, or eliminate 1 variable with any 2 equations, eliminate the same variable with any 2 other equations. Now, why would I want to do that? Because what you just did there is you created a 2x2 linear system. If you created a 2x2 linear system, that means you can solve it. You can solve it using Desmos even. You can solve it by hand. You can solve it using Desmos. It doesn't matter. I'm going to solve it by hand, clearly, right now. But you could. Once you have a 2x2 linear system, you can go to Desmos, plug it in, get your x or y or whatever. Okay? After that, boom. You can plug in your last remaining third variable. So let's go through an example. This is a nice, scary example here. It's not that scary. First things first, let's label it 1, 2, and then 3. Okay? There's many, many, many ways to do this. Okay? So I'm going to just show you perhaps the fastest way, at least to me, how I did it. I first looked at 2 and 3. Now look at 2 and 3. And I want you to try to think, why would I want to do that? Perhaps it's the easiest because all you need to do is just multiply by a negative. Which variable do you think I'm going to try to eliminate? Of course, the y's, right? So I'm going to do 2 and 3. So 2, let's multiply just 3 by the negative. So 2 will stay the same. Does it matter which one I multiply by the negative? No, it doesn't. It doesn't matter. So I'm going to do a negative 2x. Actually, I want more room here. So let's actually multiply this negative up here. What will that look like? Okay, so if I multiply this negative, that would be, let's just do the whole thing. So negative 2x is all the signs change, right? Negative 2y and then plus 3z and then equals 13. So that's what it would actually look like. And then, of course, we add. So then what do I get? So the x's don't go poofy, but I do get a negative x. The y's go poofy, which is exactly what I wanted, and this becomes a plus 2z equals 5. Now you noticed I did my z's with a line in it because I get confused with my 2's and my z's because I write really fast. So that's why I put a line through my z. So now, does that help me? I mean, I don't really do anything. All I did was step 2. This was technically step 2, guys. All I did was eliminate, there's no bonus here. I can't eliminate 2 variables, all right, at least in one swoop. So add any 2 equations to eliminate a variable. I chose y. Step 3 is this, and this is what step 3 will be. Now we're going to choose any 2 different equations. Does it matter which equations that we choose? I mean, seriously, does it matter? Honestly, no, it doesn't matter. I'm just going to show you what I did. I did 1 and 2. Now, why would I do 1 and 2? What variable do you think I'm going to eliminate here? You should be thinking, why? Why do I need to eliminate y? Because I want to eliminate the same variable. Okay, so I need to look at any 2 other equations and eliminate the same variable. That's the trick. This is probably the hardest part, 3, I think is. Because they forget, students often forget, we're going to chill this one right here. We can't do anything with the x and the z right now. But what we need to do is do another, okay, we need to do another 2 equations to eliminate the same variable. So if I look at 1 and 2, I can eliminate y by multiplying 1 by 2. So that's what I'm going to do. I'm going to multiply 1 by 2. So this is 8x minus y plus 2z equals negative 20. And then my second equation hasn't changed at all. So minus z equals negative 8. Okay, and so now when I do this, okay, what I'm going to have, my new equations is 16x minus 2y. This is my new number 1. My new number 1 when I multiply through. Don't forget to multiply to literally every single term here. Okay, every single term. Negative 2y and then plus 4z. And then this is going to be equals negative 40. Okay? And then, of course, my second one didn't change at all. So don't think, and then we're going to add. Don't think when we get to this step, oh, I'm going to multiply by 2 by, just multiply the second equation by 2 so I can eliminate the z's. That does nothing for you because then you would get an x and a y equation, but you can't solve an x and a y equation when you have just an x and a z equation. You can eliminate the x's, but then you're still stuck with an unknown of y and x. Okay, so you need to logically think. Imagine that in math. Logically think, how can I eliminate certain things in order to get my outcome? That's what logical problem solving is. Okay, when I structure it this way, I add, so this is 17x, the y's go poofy, this becomes plus 3z, and this becomes negative 48. Now that I have this, look at these 2. Okay, look at these 2. Let's cloud them. Okay, I can now look at them and actually perform 4, my 4th step, a 2 by 2 linear system. Why? Because they have the same variables, x and z. Now, if you did plug this into Desmos, you would have to change that z to a y, okay, because Desmos does not render it z. So if I go over here and I actually just plugged in these 2, if I do like x plus z equals 7, that doesn't do anything, okay, because it only supports x and y. So you would have to change that z to a y for it to do anything, okay? Now you could do that, but if you're given fractions, then you're kind of screwed anyways because then you have to do it by hand no matter what. I'm going to do it by hand no matter what. Let's not waste any more time. How do I do this? Let's stack them. So I have negative x and then plus 2z equals 5. And then I have 17x plus 3z equals negative 48. Now, this is what I have. The best way to do this is elimination. There's multiple different ways that you can do this. I'm actually going to probably multiply this first one by 17. And I know that kind of sounds weird. I just don't like multiplying two equations. Like, that's really what I don't like doing. So now, what are my new equations? This is negative 17x. This will be negative plus 34 plus 34z. 17 plus 17 is 34. And then this 17 times 5. 17 times 5 gives you 85. Okay? So now my second equation, I haven't done anything. So now I'm eliminating x. So I haven't done anything, And so now let's go for it. Let's go for it. So what is my new equation? That goes poofy. This becomes 37, not x, 37z. I eliminated x. And then this becomes, I think 37. Yeah, 37. Which is really nice. Because when I divide by 37, divide by 37, I get z all the way down here at the bottom equals 1. Now, a lot of work for just one variable, right? But now, think of it like this. If you ever watch The Office, this is awesome. I use this illustration all the time, guys. Think about it like this if you ever watch The Office. There is an episode in which Michael makes this, Michael Scott in The Office, the show, the NBC show. He makes like a kind of, I don't know what it's called. Like, he puts like paper boxes up and it's like, I'm going to go down to the basement. But he's really not. He's just kind of like, kind of doing that thing. Where, you're kind of like walking and then you're kind of getting lower and lower and lower. And then he walks back up. So he's really not going to the basement, but yeah. So, funny episode. Think of it like that. You are literally breaking down. Okay, you are breaking down the equations to get to one answer. And once you got that one answer, now what do? You have to come back up, of course. Okay, so do I plug z equals 1 into one of the original? No, follow the steps. Use substitution to find the third variable. But do I just do that straight up into the original 3? No. So my fifth step is to choose one of the previous 2x2 systems that I came up with to find the other variable so that I can then use those two variables that I would find and plug in for my original. So does it matter which one, this one or this one? I'm going to choose this one because it's a little bit easier. So negative x plus 2 times my new best friend that I found, 1, equals 5. So negative x equals 5 minus 2. And then negative x equals 3. So x equals negative 3. So that is my equation. That's my variable, okay? So now, what do I do? What do I do is now take x, now take z, and plug it into, doesn't matter which one. I see this one is probably the easiest, less numbers, so I'm going to choose that one. So now, what is my x? Well, it's negative 3. What is my y? I don't know my y, so plus 2y. Minus, what is z? Well, it's 1. Equals negative 8. Let's solve. What do those two combine to? Negative 4. And then this is plus 2y equals negative 8. I add the 4 over, so that is 2y equals negative 4. And divide by 2, so y equals negative 2. Perfect. What is my final answer? All the way up top, what is my final answer? Negative 3 for x. My y is negative 2, and my z is 1. That is my three-dimensional intersection point. Perfect. Okay, so that one was a little bit more involved. Okay, this is why I'm giving you only 3 questions on the homework quiz for tomorrow and 30 minutes. So I'm giving you 10 minutes to solve each one of these. And I've given you really easy ones. So let me tell you, just saying, I've given you easy ones. All right. So that is how you solve that one. Let's get to another one that's actually very, very, very simple. Ready? Let's erase. What if you have a hole in the equation? So if you have a hole in the equation, what does that mean? Pick one of the equations with what we call a hole to be the first equation of your 2x2. Then you're going to add the other two equations together to eliminate the same variable in the hole in the first equation. Solve that 2x2, and of course use substitution. So what will this look like? We have this equation. Of course, as always, we need to label. So first, second, and third. Now notice, this doesn't have an x. That doesn't have a z. So that means necessarily, okay, there is a hole. Now, how do I do this? Well, pick one of the equations with a hole to be the first equation of your 2x2. So what I'm going to do is actually pick number 2. So I'm going to pick number 2 to be the first equation to be my 2x2. So that means I have a y and a z, which means I need to pick the other two equations and eliminate the same variable in the hole in the first equation. So which variable is missing in the first equation I picked? X. So what does that mean? For step 2 then, I need to actually choose 1 and 3, and I need to eliminate the x. So I need to eliminate the x variable here, so then I only get y and z left over. Okay? So let's do that. So I have negative 3x minus y equals 6. Okay? And then my next one I have for third, x minus 2y plus z equals negative 4. Now, of course, I need to eliminate the x, right? That's what my equation, that's what it says. Add any two equations together. That's what we're doing. Eliminate the same variable. In this case, it was x, okay, with the hole, because that's where it is. X is missing here, okay? We don't have it. That's x, all right? So now that we discovered that, we're going to go over here. And I need to figure out how can I eliminate x. Well, I need to multiply this by 3. Okay, so when I multiply this by 3, what do I get now? My first equation stays the same. It doesn't change at all. Look at my nice, neat work, guys. My third equation does change. It's 3x minus 6y and then plus 3z equals negative 12. Now I can actually add these together. X's go poofy. This becomes negative 7y. I don't have a z here, so what does that mean? It doesn't matter. I just plus 3z. I don't have a z to combine it with. It's basically 0z, right? So I just kind of bring it down, and this equals negative 12. All right, so I have this. Great. Now notice, watch. This is y and z's, right? This, for 2, is y and z's. Solve this 2 by 2. We are now in step 3. Okay, so now step 3, my second equation we can bring into the game, y minus 4z equals 8. And then my third, it's actually not my third equation. It's just my brand new equation that I'm going to bring. Let's call it the red equation. I'm going to put it right over here. So this is negative 7y plus 3z equals negative 12. Okay, now how can I add these up? I think it's very easy. You can eliminate your y, so I'm going to multiply by 7 here. So now my new equations is 7y minus 28z equals 56 when I multiply 7 all the way through. And then this, of course, right here doesn't change. It just stays the same, right? So plus 3z equals negative 12, okay? Or negative 7y. This goes poofy. I'm left with the z's, so this is negative 25 z. And what does this equal? Oh, okay, I see what I did here. Okay, I made a mistake. It's okay, I'm a math teacher, I make mistakes. Right here, what did I do? I just dropped down to negative 12. Of course, that's not right. So this is actually negative 8. So this right here is negative 8. And then when we add, this will be negative 8. Or just be, wow, I'm just really bad here. I'll do all my, changes in purple here. It's not my day of adding. I'm saying negative 8, and I'm so stupid. This is just negative 6. Pretty sure this time it's negative 6. So in purple is my changes. This is not negative 8, negative 6. This is not negative 12, negative 6. So now this is 50, okay, which means z equals negative 2. Okay, sorry about that. Like I said, I make mistakes too, and sometimes I make them twice, okay? So, boom, I caught it though, I caught it. So, now negative 2, so z equals negative 2, I have that. Now I can just start performing my substitution, so my fourth step, just kind of building back up again, right? So how do I do this? Well, it doesn't really matter. I can plug z probably into my original second equation now that I have just two variables, and I plug z in, I just get y. So that's what I'm going to do. So y minus 4 and then times negative 2, this equals 8. So y plus 8 equals 8. So that means y equals 0. And now I can plug it into whatever. Let's just plug it into the first one even. The first one, because I already know what y is. So negative 3x minus 0 is just 0. So I'm not going to actually write that. And then equals 6. So x equals negative 2 as well. Awesome. What is my final answer? Negative 2, 0, negative 2. Boom. Okay, sorry about the whole delay with the 6 and the 8 and everything. That was my bad. Awesome. I have one more example, an example that's actually a word problem. So let's get to it. Make sure you have all this down. So this is an actual application question. It's a great application question. You'll see it definitely on your final exam. And I do mean your final exam, okay? So a Broadway theater has 500 seats divided into orchestra, main, and balcony seats. Orchestra seats sell for $40, main seats $30, balcony seats $20. If all the seats are sold, the gross revenue of the theater is $14,300. If all of the main and balcony seats are sold, but only half of the orchestra seats are sold, the gross revenue is $12,300. Now, how many are there of each kind of seat? So basically what it's saying is, what are the seats? Okay, how many? Like, how many seats does each one have? There's 500 seats total. I want to know how many main, balcony, orchestra. Okay, so that means I'm going to be using O, M, and B for my variables. My first equation, okay, is going to be O plus my main plus my balcony equals 500 seats total. That's the first thing I'm given. Okay, right here. So I'm going to use that sentence to my advantage. The second one, orchestra seats sell for $40 per seat. So that means I have $40 per orchestra. I do a little O for orchestra. Try to keep up right there. And then plus 30 for main, so 30 main. And then plus balcony seats is 20. So that means 20 per balcony seats. Now, if all the seats are sold out completely and utterly, this equals $14,300. Fantastic. Now, my third and final is almost the exact same. If all the seats are sold, it's 14,000. Or sorry, I already said that. So if all of the main and balcony seats are sold, but only half of the orchestra seats, the gross revenue is $12,000 here. So what does that mean? That means only half the orchestra seats. Well, what's half of 40? Okay, I can just take half of it, right? So that means just 20. Okay, so 20 orchestra plus, and then the other things remain the same: 30 main, 20 balcony, but it's a different revenue. So I actually don't make 14,000; I make 12,000. specifically 12,300. So now I have this. Now what do I do? How can I try to find a bonus? Is there a bonus at all? And in fact, there is. Okay, there is a bonus, and it is M and B. So I can actually multiply any equation. In this case, I'm just going to multiply the third equation to eliminate M and B. So if I multiply this third equation, okay, what happens is this negative gets drafted in, like distributed in all the way through. Okay, I'm not going to show that step. I'm just going to go straight to here. So there will be 20 orchestra seats left. Why? 40 plus a negative 20 gives me 20 orchestra. Now that will go poofy. These will go poofy because they're negatives. And then this also gets a negative. So that means equals, what's 14,300 minus the 12,300? Well, that's just 2,000, right? Okay, which means when I divide, my orchestra seats are 100. So that one was easy because it's a bonus, right? That's awesome. We want that. So now let's look at two others to follow my steps for the bonus steps, 1 and 2. If I look at 1 and 2, what do I have? Well, 1 and 2 are kind of similar, and I need to basically eliminate the same variable. So let's eliminate or a different variable. I don't want to eliminate the same variable. Well, I could eliminate M and B, but I don't want to eliminate the same variable that I found. That's what I'm trying to find. That's what I'm going to try to say. I don't want to eliminate O, so I can't do O. So does it matter which one I do? Well, no. I guess we can try to eliminate probably B because it's easier. So let's try to eliminate 1. So let's multiply by negative 20 all the way through. So it eliminates that B value. So if I multiply 1 by negative 20 all the way through, right? Multiply by negative 20, I get negative 20O. Okay, and then minus 20M, and then minus 20B, and then equals negative 10,000. Okay, and then of course my second equation stays the same. I don't want to eliminate O because I want to plug O in, my orchestra, and then plus 30M, and then plus 20B equals, and then this is 14,300. So now when I add these, that goes poofy, the B's go poofy. This is going to become 10M and then 20O. And then this actually equals 4,300. So now what I can do is plug in my O. So what's 100 times 20? That's going to be 2,000. And then plus 10M equals 4,300. And then as I start solving, this is 10M equals 2,300. And so M equals 230. Okay? Now, of course, I can go back to my number 1 and then find out the rest of the seats. 100 orchestra plus 230 for main. And how many balcony? I don't know. I'm going to find that out. But total, they give me 500. And so when I do my math arithmetic, balcony is 170. So I have 100 for orchestra. Main, I have 230, and then B, I have 170. They should all equal 500. Many, many times I have students giving me like 500 for orchestra, 70 for main, and then like B is like 1,000 seats. It was something like that. I'm like, are you serious? It literally says in the problem there's only 500 seats. You're trying to find how many seats. Literally, look at the problem. So I have 100, I have 230, and then of course I have 170. And that is my final answer. Sweet. So I know this was a long lesson. It was a lot of algebra. I get that. So go through the lesson again. Try your homework. Go through the viewing examples. Try your very, very best. Okay, what did we learn? We learned how to verify the solution of the system of linear equations in 3 variables. And we also solved systems of linear equations in 3 variables while solving problems using systems in 3 variables, like models, applications, and stuff. Homework quiz will be tomorrow, guys. It's 30 minutes, 3 questions. Feel free to email me if you have any questions, though. But until then, this is C-Squared Mathematics. I'm Mr. Carlson. I hope you guys make the best day ever. Make good choices. See ya.